So I'm talking about our experiments, and this has to do with quantum computing, as also do with quantum thermodynamics, and that is what I'm going to present. Here you see in the background our trap, which we are using, 32 segments. We shuttle the ions, I show you all this, and here is the menu of my talk. So first of all, I want to talk about how we are intending to scale up to have in 1.5 years 50 qubits. Now we have a handful, like 10, okay, up to 10. But we have another architecture in mind. We call it eQuan, that is ion trap quantum computer with Anbindung. That means connection to a high-performance computer. So it is good for hybrid quantum computing, especially in the sense that we have seen the last talk already, kind of the quantum computer is just a coprocessor to a high-performance machine and operate this. For quantum error correction, which I will briefly mention, we need in-loop measurements and feedback, and I talk about this. But for quantum thermodynamics, you need qubit thermalization also. So we talk about the spin degree of freedom of the ions. So we are going away from the pure states, up and down and superpositions, but we go to mixed states, and these mixtures can be prepared to investigate quantum fluctuation relation theorems, to make heat engines work, quantum heat engines or heat engines approaching the quantum regime. It's really a big word to say I build a quantum heat engine. We did not, but we are approaching this. And there is also tests, kind of specific tests, which are thermodynamically inspired tests of quantum computers, where you have a computer and you have a heat leak and you detect this heat leak by means which you could not do otherwise. So start with the scalable architectures. Typically you hear the number of qubits. That is only one number. If you cannot connect them, it does not help. So the ion traps are famous for all-to-all connectivity if the ions are sitting in the same potential. So that is a high connectivity which you get, which gets you with a high fidelity, and ion traps are known, and I think you will dwell on this, for high fidelity of gate operations. So all these things together give you big volume, okay? And then on top of you need a good preparation and a very good readout fidelity. Last talk we heard, if you want to quantum error correct something, you should trust to your syndrome readout. If you cannot trust to it because there's fault, you are in the middle of nonsense, okay? In loop qubit readout is also nice because you have kind of separated ions and you can read out here while you can do the interactions there without doing harm. Real-time feedback, we heard about FPGAs, which do this really quickly within the loop, within the coherence time of the ions. And last not least, you want to connect to a high-performance computer in order to make this hybrid computing possible, okay? So to bring these things together, high number of qubits, high connectivity, and high fidelity, you need not only to optimize the number of qubits and connectivity, because you generate a big mess in this way. Everything is interacting with everything, that is a big mess, okay? Then you have problems with controllability. So architecture means you have small roads which go to every house, but then you have bigger houses which connect to these roads, and then have even bigger roads which have not a lot of exits, but just have a few exits. So that is kind of this architecture which you have to think about. Go back to the qubit which we are using. This is the optical qubit. And of course, there are an upcoming number of groups, so I cannot keep track. Maybe there are some wrong things here, but optical qubits was the first qubit to do it. You have a ground state, you have a metastable state. You do this with a laser and generate superpositions. And the readout is just beautiful because here you can scatter photons whenever the state is projected into the ground state. However, it is projected in the D5 half state, you just see no photons. So dark or bright, a wonderful separation of qubit readout, and we reach something with 4 nines or so. If we really try a bit harder, we would go even for a 5th 9. But here, the optical phase stability of this laser is important, and you have a limited lifetime. So that is the problem of this qubit. You can go to hyperfine qubits, living now completely in the ground state, so infinite T1 time, perfect, but kind of a complicated level structure. If you now do the spin qubit, you have only the electron spin pointing up or down, and that's the qubit. So the whole ion is only there to keep this spin in place, I would say. And we're doing basically the computation with only this outermost electron, flipping spin up and down. And that is done by a Raman transition, also like here, without problems in phase coherence, and you just have magnetic field fluctuations which might affect you, but you can kill them. For the readout, you go to the optical qubit. So this is all basically interconvertible. So you can also choose your qubit and do it kind of spin qubit first, hyperfine then, and so on, whatever you like. So we do this one in calcium 40. Now, architecture. There is one archetype of architecture that is you have a linear ion crystal and you're addressing single ions, and that makes you connect these ions via the common motion of vibration. That's what we will hear in the next talk also extensively, I guess. And these big companies are along this road, and Chris Monroe and Rainer Blatt, and there are many, many citations I could put on top of it, okay? So here you can trap stably maybe 20 ions. I don't believe you could go to 200, but maybe it ends already at 30, because then you are creating more mess, because you are having addressing errors, you have crosstalk, all this kind of crazy things which happen, and with that lowers your fidelity. So then you have to think about a new architecture, and that is what Dave Weinland came about. He said, let's shuttle these ions always in the position where you do the gate operation, but don't do this with all the ions, do it only with those ions which you want to address, and the other ones can be safely stored at another place. So you need a more complicated trap structure to do this. You need to learn how to shuttle these things, but then in principle it's scalable. Now in reality, this Roman emperor thing, divide and conquer, that is of course the principle of this idea. It takes time because you have to shuttle these things and then shuttle back, and you are kind of not ending by shuttling. And in our case, 90% of the time is used up by shuttling and only 10% by the really thing a quantum computer should do. So yeah, this has some drawbacks also, I have to say. And so we come together with an architecture which is addressing and reconfiguration operations. So it has basically the architecture of an addressing beam set up here, 10 foci which do this addressing, but then you can shuttle this whole ion string out, reorder it, mix it with other fresh ions from the side, and then you can shuttle this whole bunch of ions into the addressing zone again. So it's kind of a piano player playing very quickly with his fingers here. Now you want to go to another key. In our case, we move the keys instead of moving the hand. So that's what we do. Multiple zones for addressing, register, and we are thinking we can go to 50 or potentially to 100 qubits there. And this is all based on scalable things which are coming from industry. We have BMBF money. We should really build a quantum computer that works 7/24, really reliable. And we have also the HiPC connection to Mogon that is just on the other side of the road. And we are aiming for quantum chemical calculations together with a company Covestro that is doing polymer physics. So that is our plan. We are building this up. So in 1.5 years, I hope I can show you 50 ions in this scalable approach, maybe even more, I don't know. We will see. We promised this at least. So that is our web page. This is where you can go, and then you can type in your code, basically. You can go either on the website, drag and drop, or you send in the penny lane code or whatever you like, address it also via the high-performance computer. Then it's compiled. The circuit is kind of casted into our native gate set and optimized for this specific ion trap Hamiltonians that you can realize. And then we need to shuttle these ions also. So that is the shuttling compiler and the quantum compiler that is then going to a manager addressing now all the instrumentation like the radio frequency sources, DC voltages, and so on a much more kind of C++ platform here that takes into account basically all the hardware, including programming the FPGA, what it has to do, and so on. Okay, this is now what the circuit optimizer does. You enter some random circuit, you run it through the circuit optimizer. Typically, you gain a factor of 5 in reduction of gates. It's kind of, and you make it into the native gate set, and then the shuttling compiler calculates what ion should play what role of what qubit and brings it in the segmented trap. That's time running by, and that are all the positions that you can take in your trap. You see these ions are starting here, and there are 4 ions here in this algorithm, and then they go together to do a gate operation. This is in the laser interaction zone here. Whenever you want to do this, then you can do it. We have not these 10 ions in the laser interaction zone at the time. Now we have only 1 or 2, so we can do 1 or 2 bit gates, but we can also combine with different ones and so on. So that was...
I have a question. Do you plan also, are you also able to do operations in parallel?
Yes, sure, absolutely. If you go to the IQ1 architecture, you have seen 2 addressing zones. So you can use one addressing zone for addressing, the other one maybe for readout. Then you can do at the same time some reordering. So that saves a lot of time. Thank you for this question. Absolutely, yes. So far we do everything sequentially, which costs an enormous amount of time. Yeah? So I hope I can run this video now, because that shows how we can operate this trap from outside. And here the president of our university, at the occasion of the 75th birthday of the university, he shows our quantum computer. This is now in Berlin, and he shows it. So he puts this drag and drop thing together. You see in the background, this is of course what he cannot see, but we can see it. Here are the 2 ions which have to play the job. He puts a C0 here, or a C phase actually, some Hadamard operations. Now, this is kind of simply just the matrix multiplication is done.
Details zu
that
gehen.
is what should be the outcome.
Steht den ganzen Abend für Sie zur Verfügung.
Deswegen
hat sich hier vorne hingesetzt, Sie alle wissen, wo es ist. Aber ich kann das jetzt, da steht Run, das heißt, das wird jetzt nach Mainz geschickt, das wird dort im Quantencomputer verarbeitet. Und das, was wir hier sehen als Orange, ist das experimentelle Ergebnis dieser Quantenoperation. Ausgeführt mit einzelnen Ionen unter dem Einfluss von Laserstrahlen. Wir lassen es mal so stehen, Herr Schmidt-KALER.
Our experiment by the president can really fail, and there were a lot of other people in the room. But now it is really nice. We have a collaboration with Covestro from Leverkusen. They log into this web page and they do some tests with this, whether it works or not. Okay. Okay. So this is our architecture which we have now. This is the now place. Only 2 ions in the laser interaction zone. We can separate ion, we can turn the ions like this, we can move ions quickly, and so on. And we have the radial mode to use it for the geometric phase gate. And that is the fidelity which we reach. The single bit operations have really low errors, a few fraction 10 to minus 5. I think now this went down to something like 3 10 to minus 5 at the moment. So that is, this could be improved. I would be so happy if this would be a 9 here instead of an 8. But yeah, we know what we have to do actually. Okay, now what do we do with this? Topological quantum error correction, we heard about this. How does it work? Don't get it wrong, the ions are still sitting in a linear arrangement in the trap, but it's just for a theory purpose that you plot this as plaquettes. So you have a plaquette of 4 ions, 4 ions, 4 ions, altogether 7 ions make 1 logic qubit. So you measure the stabilizer and the red plaquette, hopefully you get a 1, then you are happy, all are showing up, so to say. The parity check is showing nobody's wrong. Then you do the stabilizer measurement in X and Z direction. In the blue plaquette, maybe this is also everything is okay. Then you know the one who does the error is only possible if the green plaquette shows a stabilizer output of -1, then you are sure this is the bad guy because he is only shared by the green plaquette. So this is kind of my simple-minded topological quantum computer, quantum error correction. And here are the data qubits like this. We do it only in the red plaquette now so far. So you have these 4 data, and you have to do a fault-tolerant readout of this plaquette, of the parity. So you do it to have all these phase gates here to the error syndrome here, okay? But now the error syndrome can also do some mistakes. Say there happens something bad to this qubit here. which can happen. It's only a qubit, actually, what we use for readout of the syndrome. So it's as faulty as the other guys. So you should really be sure that you don't listen to this qubit when it did some mistake. It's really bad, because then the error feeds back into the data, and then it becomes uncurable by this distance 1 code. So it's really dangerous. If you have some problem, then you fall into deep problems. So you better check it out whether the ancilla readout is really reasonable by a flag that makes the readout of this plaquette fault-tolerant, or to some degree fault-tolerant, because you check out with a second qubit. Now, let me show, time is running this way. You start out with the 6 qubits. There are the data qubits, and there are the fault-tolerant readout by these other qubits here. And then the sequence runs through 90 configurations. So we shuttle around the ions, and always sometimes we do gates and whatever. There's a couple of splits and rotations and so on. And we do the gates, and that's the readout. That is the result. You see, we just run our code on this one plaquette, and the single shot fidelity is 92% here. That's the blue bars. That is, you see, these are the parity states, 0, 0, 0, 0. That is a good one. This is also a good one. This is a wrong one, okay? This shows low. This has only one 1, okay? This has also 3 ones, is also low. These are high. They are the good ones, okay? So can select between the good and the bad ones in a very nice way. And now, why is this flag? You see, the flag has been raised only in a very few amount of moments, because it is mainly read out the data which we send, and the data was good. So why should the flag show up? Now, if we do the post-selection on the situation flag has been not raised, the readout, the single shot fidelity goes from 92.3 to 93.2. It's not a misprint. This looks like a little tiny effect. You see, there is only going up a little bit. The green is a little bit higher than the blue, but it's an improvement by 4.5 sigma. So it is significant, okay? So it is important to have this flag on board. It really does something good. We can also check this by putting in one error by hand, insert an X or Y rotation here on this syndrome. And then you see, in some bases, you would not see it on the data, because you measure them in the bases where you cannot see it. You cannot see the phase shifts. You can only see the Z-axis. So then you have errors, but you think you are right because you're measuring the wrong bases. That would be really completely horrible. But with the flag, you always detect this. So you have a 90 or 88% detection that the flag really helps you to solve this problem, okay? So you see, these numbers are still not 99.99 something. So error correction is not yet really helpful, in the sense that you would not be more happy to just keep the qubit alone. But it is at least the algorithm which is working and shows the right features. So now I'm going to the other part, and now I want to combine this coherent interaction, like the gate operations, the 2-bit and 1-bit gate operations, with incoherent operation, and that is important for this quantum thermodynamics and for investigating the fluctuation relation theorems and so on. Heat engines and test against heat rate, and also hybrid circuits. We heard from you just the other day that it would be nice to put erasers and measurements and all the thing into a circuit. And of course, we have to be prepared to do this, okay? So we have to kind of cancel information by, or do some rotations which do this, yeah? Resets and so on. So this is in preparation also for this theory work by Yamir and Kelly. So how do we prepare in a thermal state of our qubit spin? We just do an incoherent pumping, so to say. We have our state 0 and our state 1, and if we do an optical pumping, which is not perfectly with sigma plus light, but a little bit of pi light, then you get pumped into both states, and we are, according our definition, is kind of the NMR temperature. So how much is the spin really polarized? Is it going to the really ground state 0, or is it only a kind of a thermal mixture of 1 and 0. And that you can control very accurately. And then you have the way to thermalize a kind of spins to a very cold bath situation and some of them to a very hot bath. And you have work ion, which does sequentially gate operations, little bit of gate operations with the hot and the cold. And you see this is also looking like a steam engine. And that delivers some work, which is then going to another ion, which is kind of the load, where you deliver this energy into. So this is our little steam engine, which we have in mind, which can be run then on a quantum computer as a quantum thermodynamic process. And the interesting thing is, of course, that you will have entanglement after a while between the heat engine and the reservoirs. And then when everything became entangled, the engine stops working. So that is what I'm really eager to see. Okay, now let's look into this work fluctuation in slow processes. There was a paper by this group here of authors, and they discussed that you can have a classical work fluctuation dissipation relation, and this is just excluding this Q. That's kind of the classical part. But if you have non-commuting operators, then you have always some sort of quantum projection noise, I would call it. It is, in my experimental language, it's as simple as this, that you have some quantum projection noise because your operator is not commuting with the measurement axis and your rotations are not in the right direction, so to say. That means you are measuring in a rotated basis, and that gives you some noise, additional noise. And this accounts for this QW. And you see the classical part is this blue one. So that is this blue part on this side, the width of the fluctuations, how broad is my work distribution. And the work, that's this one. And you see a gap opens here for very low temperatures, a gap opens, and that is exactly this QW. That is this leftover, which is due to the non-commuting operators. So I think nobody has checked this so far, and we have now prelim data about this. So in this team, we are doing this. The recipe is you prepare a thermal state to start with, because we know for low temperature it should show up. For high temperature, it should go to the classical limit here. Can I go back? No, only once. So for high temperature here, there is no difference, a very tiny difference, and only for low temperatures here it shows up. So you want to change the temperature, you want to prepare different thermal states, and then you have to repeat kind of a protocol, a protocol where you do a two-point measurements. You measure after thermalization, then you do some rotation, which is not permuting, and then you measure a second time, and from this you get the work distribution, and from this work distribution you calculate what is the QW. And you see our data show for large beta, which means very cold, you get a deviation from the classical setting. Okay, you get really this QW, which increases when you go very cold. I think it's a nice result to show that this work dissipation fluctuations have to be changed if you're in a quantum regime. So this is affecting a lot quantum thermodynamic engines, I think. Now, about quantum thermodynamic engines, you can be inspired by this type of test. You know, if you test your car, they don't check the motor in detail. They don't do gate tomography and kind of randomized benchmarking with your quantum computer, with your car, but they just put it here and they look what is the kind of exhaust. So it's a thermodynamic test instead of a detailed, whatever, looking into detailed test. And only if it fails here, then you check this. So we have been inspired by looking whether you could check heat leaks, just looking thermodynamically at the system and not looking into detail and checking every qubit, whether it's going right or not. And this is inspired by the work of Ram here, Ram Utstein. He's doing passivity-based tests, which are kind of an extension of the second law of thermodynamics. And then you can check these things. And there's also work by Norbert Linke and team here in the same direction. So what can you check? If you have a completely closed system, that is the ideal quantum computer, completely Hamiltonian dynamics, no dissipation, no problems, no pain, but that is not the truth. You have typically noisy control fields which are making your Schrödinger equation different from pure states and the unital evolution. So basically you can do a spin echo and then it's gone. So that is my experimental point. I would say you have a noisy control field. If you do it clever, you can spin echo it away. But there is another thing, that's these open quantum systems, and they have a coupling to another unknown qubit, to an environment, a real coupling to an environment. And now if you trace over this environment, then this information is really gone. You cannot undo it. That's really gone, and that shows as a heat leak, okay? This exchange with the environment. Now we have, basically RAM has conceived this kind of simplest case of algorithm, where you have a code and an environment qubit, and you run this algorithm along the time with a gate, a C0, the phase gate, and here a swap. And if you swap this, then you have a leak. If you don't swap it, you have no leak. And the cool thing is you could show that this testing of the passivity deformation is sharper as compared to the second law of thermodynamics. And we see here a leak. Whether we don't do this swap, we don't see a leak. And that's the end of my talk. Sorry for being a little bit over time. So I think these trapped ion platforms are well suited, scalable architecture, have nice fidelities. You can control them also future. I think there will be a moment when a theoretician team comes and say, could I use your computer for special tests and run my algorithm on this? And then it is kind of experimental physics and theoretical physics are completely merging at that moment. And that's why we have this user interface. But we need not only this high fidelity coherent operation, kind of the standard set of a quantum computer, but we need also on top of it some fast thermalization, employ work cycles, and kind of making it more versatile for different protocols, which are not the standard protocols like Grover or whatever you think of, okay? So at the end, this will be free programmable and also hybrid, including dissipation, quantum circuit handler, where you can go into multi-particle entanglement. If you're interested, go to this webpage, you find all of my papers. Thank you for your attention.